Calderon-Sigmund class of singular integral. Second, we are going to discuss the development of the Gaussian singular integral. The Gaussian Ritz transform, the higher order of Ritz transforms, and we will discuss the boundaries property. Then we will introduce the generalized Gaussian singular integral and study the mention the boundaries properties of them, including the Gaussian variable of X spaces. Then we will consider alternative Ritz transform, where interesting result. And then finally, we will introduce a new class of Gaussian singular integrals that we call generalized alternative Gaussian singular integrals. With this, with the generalized Gaussian singular integrals and the generalized alternative singular integrals, we complete a general, a whole family of Gaussian singular integrals. Okay, so singular integrals are one of the most important operators in classical harmonic analysis, and they appear naturally when you take convolution with a non-integrable kernel. So you can use Young's inequality to study LP continuity. They appear naturally in the proof of the LP convergence for Fourier series. That is to say, you want to prove this for a function f in LP of the one-dimensional toroid. And in order to prove that, it appears naturally this operator that is called the conjugated function. And as you can see, here you are taking a convolution with a kernel that is not integral. And what we want to prove is that still it is an LP bounded operator. The original proof of this was by Marcel Ries in 1920 using complex methods. But our approach, following the Calderon-Sigmund school, is using real methods. Right? Of course, after the conjugated function, there was the one-dimensional Hilbert transform, which is the extension of that case to non-periodic case, in which instead of 1 over 2 tangent of x over 2, we use 1 over x. So this is what we get. And then you pass to d dimensions, and that's what is called the Ritz transform. In this kernel, is singular at the origin. Later, that was generalized for convolution kernels of this form, where this has very special properties. So, like if the omega is only defined in the unit sphere, and its integral over the unit sphere is 0. Then Calderon-Sigmund in the 50s introduced what is now called the Calderon-Sigmund transformation, singular integral, that later were further expansion to any kernel that satisfies these two conditions. And then using that kernel, using the Cauchy value problem, you get the singular operators. These are Calderon-Sigmund operators. Okay, so very schematic. This is what is the story of the classical case with respect to the Lebesgue issue. What about in the Gaussian world? So, as the title says, we want to go through the looking glass. So, instead of the Laplacian, we have the orthogonal operator that is one half the Laplacian, but you have this drift x times the gradient. This operator is very special in the sense that, for instance, its spectrum is a point spectrum, and the Hermite polynomials in V variable are the eigenfunction of it. And it's related with the Gaussian measure precisely because it's symmetric. Because when you put the Gaussian measure here, you have this, it's easy to prove by integration by part, you get this. So if you are working with the Gaussian measure, you can work with the Laplacian, but with the orthogonal operator, because that is the symmetric Laplacian in the Gaussian group. Now, that operator, I mean, you can consider the annihilator operator, that is basically a rescaling of the usual derivative, but that derivative is not symmetric nor antisymmetric in L2 of the Gaussian measure. So the formal adjoint is this guy that is called in quantum mechanics the creator operator. Then, using those two operators, the orthogonal they can be written, or negative orthogonal they can be written in this way. This is very important for we are going to talk later. Now, in the case of the classical case, if you take using the Fourier transform, you can see that the risk transform can be obtained taking the derivative of the inverse of the Laplace. Well, doing the same here, where this is the derivative, our Gaussian derivative, and then instead of the Laplacian, you take the orthogonal, and then you take the inverse of the square root of pi. That is, morally speaking, the risk transform, of first order risk transform, and from the fact that the Hermite polynomials are eigenfunctions of the orthogonal operator, it's easy to check that the action of the J risk transform over the dimension of Hermite polynomial is written like this. So there is you get some translation in the order of the polynomial. And it can be proved that you have, this is the kernel. So this is this kernel. But it's important, I want to take a minute to see that you have this term here. And then, yes, you can prove that using that kernel, the risk transform can be written in this form. And the case, in one-dimensional case, that was obtained studied by Benjamin Mackenhoff in 1969. And he proved the LP boundedness using real analysis method, the Natanson kernel. So he was able to prove this. And later, much later, there was a lot of activity in probability. So Paul-André Meyer proved the LP boundedness of the risk transform with respect to the Gaussian measure using probabilistic method, very hard things like the Brownian motion, the famous Buchholder-Gander inequality. And using that, yes, you can prove this. And one advantage of the probabilistic method is that the constant is independent of dimension. There was another proof obtained for the risk transform in 1986 by Richard Gandhi using Brownian motion and the notion of background radiation as a stochastic process. And then James Pissier also got another method that is a hybrid method between analysis and probability, method of rotation and transference method introduced by Robert Koishman and Guido Weiss. So I entered into the picture that because following the